In the first lecture on kinetic theory of plasma, we have seen some of the introductory fundamentals of this topic, and after that you have seen what is distribution function. Actually, the meaning of distribution function we have dealt in detail in the first lecture on kinetic theory of plasma. Now, after getting the idea of distribution function f of r, v and t, we are in a stage to deal with a very important equation, or you can say the basic equation of kinetic theory of plasma. Actually, this basic equation of kinetic theory of plasma is known as Boltzmann-Vlasov equation, or you may simply call it Lasso equation. Actually, the complete theory of kinetic theory of plasma will be dealt in terms of this Lasso equation. So, today we are going to know or going to find what is this Boltzmann-Vlasov equation. Actually, you know that if collision takes place, then the direction of motion of plasma particle changes randomly. So you can say that collision of particle produces randomness in the plasma particle velocity. And if there is no any external field or external force acting on our plasma system, then the motion of the particle will be random. And when you say random motion, it means the direction of velocity is possible equally in almost all directions. And so in this condition, the average velocity of plasma particle becomes zero. Why this average velocity becomes zero? Without calculation, you can say, since velocity may be in any direction, so the probability of getting the positive and negative values of velocity will be same, and so whenever we will find the average, that will turn to zero. So in short, you can say that if there is no external field acting on our plasma system and collision is taking place, then motion of plasma particle in general will be random, and in this condition, due to that collision, the average velocity of plasma particle becomes zero. And as you know, the distribution function is actually a function of position vector r, velocity vector v and time t. So if there is any change in this parameter v, definitely this distribution function will get changed. So due to change in this velocity vector v, the distribution function f is also get changed. So now if we assume that the total time derivative of this distribution function f is equal to the rate of change of f due to the collision, it means the cause in change in f is only collision. If we consider, then if we will differentiate this f with respect to t, then that will be simply equal to the partial derivative of this f with respect to t due to collision. So mathematically you may write this equation like this, that d dt f of r vt is equal to del f by del t due to collision. I have written here collision completely, but after this we will simply write only C subscript to represent this collision. Now let us evaluate the LHS of this equation 1. LHS, you can see this is d dt f of r vt. So now our aim is to first of all evaluate this LHS. So see here, you can see this d dt f of r, v and t. As you know that this r represents actually three scalar quantities x, y, z. So instead of r you may write x, y and z. These are actually the space coordinates, you know. And instead of v, we can write the three rectangular components of velocity vector v, that is vx, vy, and vz. And t is an independent parameter. As you know, you have already studied in the first lecture on this distribution function that actually this distribution function f is a function of 7 independent variables. You can see these x, y, z are space coordinates, and these vx, vy, vz are actually velocity coordinates, and time is a parameter. So as a whole, there are 7 independent variables on which our function f depends. And you are going to find its total time derivative, or you are going to differentiate it by the method of ordinary differentiation. But you know, since our function f is not a function of only one variable, but it is a function of 7 independent variables, so to get its derivative, definitely we will have to adopt the technique of partial differentiation. And you know very well how we follow the technique of partial differentiation. Actually, whenever you will differentiate this f with respect to a variable, other variables will be kept constant. So let us see. First of all, I am going to differentiate this f with respect to t. Let us say t, although t has been written in last, but I am going to differentiate it first of all with respect to t. So you can see what will be this result. This will, when we will differentiate with respect to t, you can see this will be del f by del t times dt by dt, because finally we have to use the operator d dt, and plus. Now let us see. Now we will differentiate this f with respect to x. So when you will differentiate with respect to x, what will be your result? This will be del f by del x times dx by dt, and plus. Now with respect to y, see here, this will be del f by del y times dy by dt, and plus del f by del z, and sorry, dz by dt, and plus. Now we will differentiate with respect to vx, vy, and vz. So this will be del f by del vx times dvx by dt plus del f by del vy dvy by dt. I hope you are getting these things, because you know the method of partial differentiation very well, so you can easily understand it. So this is del f by del vz times dvz by dt, Now see, what is this dx by dt? You know this is x component of velocity, which we will denote by the symbol vx. Similarly, this dy by dt will be vy, this dz by dt will be equal to vz, and similarly you can see this dvx by dt is actually the x component of acceleration, and similarly this dvy by dt is y component of acceleration, because you know the time derivative of velocity is actually acceleration, and similarly this dvz by dt is z component of acceleration. And see the first term, here is dt, that will be simply equal to 1. So after making these substitutions, what will be our result? You can see easily. So you can see, since dt is 1, so first term will be simply del f by del t. Now instead of this dx by dt, what you will write? We can write this simply vx. This is actually the x component of velocity, times del f by del x. Again, instead of this dy by dt, now we will write Vy. So this is Vy del f by del y. And instead of this dz by dt, we will write Vz. This is z component of velocity, and del f by del z. And now I will write the last term in the next page. So see here, this will be actually equal to what? This will be plus, I am writing it here, you can easily see it. This will be ax del f by del vx. I am not turning the page because it should be in your mind. You can see here. And again there is dvy by dt, and instead of dvy by dt we will write ay. This is y component of acceleration times del f by del vy. And plus, instead of dvz by dt we will write az times del f by del vz. So this is the last term. So now you can see in these equations what we can write these terms: Vx times del f by del x plus Vy times this much plus Vz times this much. What we can write, you can easily see. Now you can see that this Vx times del f by del x plus Vy times del f by del y plus Vz times del f by del z. Actually, this result can be written as V dot del f, or gradient of f. Actually, you can check it. How it is possible, you can check it. As I am just going to clarify this term. You can see when you write V dot del f, you know when we will express this V in terms of its components, what will be this? This will be I hat Vx plus j hat Vy plus k hat Vz. I have written it at the place of vector V, you know it. Here I, j and k, you know, these are actually unit vectors along x, y and z axis. Now from the definition of gradient, this is actually gradient with respect to a space coordinate. So this del operator is in fact I del del x plus j del del y plus k del del z. And so gradient of f, you know, this is defined as I del f by del x plus j del f by del y plus k del f by del z. You know it. This is just the definition of gradient. Now take the scalar product. You know, when we will take the scalar product by I Vx to all these terms, then I dot I will be 1, but I dot j will be 0, I dot k will be 0. So the last two terms will vanish. Only the first term will remain because I dot I is 1. So this will be simply equal to Vx del f by del x. Now when you will take the scalar product by this term j Vy, then only this term j dot j will be 1 and that term will be non-zero, and apart from that all the other two terms will vanish because j dot I will be 0, j dot k will be 0. So you can write it as Vy del f by del y. And similarly you can say in the when we will take the scalar product with k Vz, the remaining term will be what? That will be Vz del f by del z. So you can see I have evaluated v dot del f and it was found to be this much. So you can verify that this expression vx del f by del x plus vy del f by del y plus vz del f by del z can be written as v dot del f. Actually, here this del operator, you know, this is defined as I del x plus j del y and plus k del z. And what is this operator? You know, this del operator actually is the gradient in the position space or coordinate space. This is gradient in x, y, z space. That is position space, or you may call it configuration space or Euclidean space or coordinate space. You can call it by several names. Similarly, now we will see this last expression in the above equation. So again, you can see ax del f by del vx plus ay del f by del vy. This is not del y but del vy. Del vy. Del vy plus az del f by del vz. Like above, you can write it as a is acceleration and ax, ay, az are actually the components of acceleration, and we can write it as a dot del vf. Del vf. Actually, this operator del v is also gradient operator, but this gradient operator is not of position space, but it is the gradient operator of our velocity space. Actually, in your textbook, you also find another symbol for this gradient operator in velocity space. We also write like this. This is written as a dot del v f. This is just another way of writing. If you are feeling convenient in writing this symbol del v, you may write it. Or if you feel convenient in writing this symbol, you may write it. Meaning is same, but only there is another technique to write, or only another symbol for this operator. So you can say this del v is also a gradient operator, but this is gradient operator of velocity space, vx, vy, vz. So here this del v, which is equivalent to del v, this is actually gradient in velocity space. When you say velocity space, it means instead of coordinate we take vx, vy, vz. And similarly, as I have checked the above result here, similarly you can check, so there is no need to check it, you can understand. And so now we will make the use of these two equations in the above equation. So see the above equation first of all. You have seen that we have actually evaluated that ordinary derivative of this function f with respect to t, and that was actually equal to this much plus this much, and we have evaluated the value of this expression and this expression in terms of the gradient operator. So after making use of these, what will be our equation? We can easily now see. So that equation was actually equation number 1. This is actually equation number, not equation number, but first of all put this, I have not put it any equation number, so you can write it as df f of rvt dt, and this is, you can see, that will be equal to, the first term is del f by del t, and for the second bracketed term we will write as you have just obtained v dot del f, you can see, and for the third bracketed term you can write a dot del vf, you can write it. Say this is equation number 2. Now we will put this value of df by dt in equation 1. So see the first equation which I have mentioned here, you can see this is your first equation. So we have evaluated the LHS of equation 1, and so we will equate that LHS to the RHS term, which is del f by del t collision. And as I have told you earlier that now we will write only the subscript c to represent collision, not the total complete spelling. So from equation 1 and 2, actually we will make the use of equation 2 in 1. So what will be our result? Our result will be del f by del t. Instead of this we will write this plus v dot del f plus a dot del vf. This is instead of df by dt. And as you have seen in equation 1 in RHS, there is del f by del t collision, and for collision now I am writing only c, that c represents actually collision. So now if you consider that F is the force acting on plasma particle and m is the mass of plasma particle, then from second law of motion, from second law of motion, you know this is a very basic fundamental, and as a student of physics everybody know it, that according to Newton's second law of motion, F is equal to ma, and you know F is force and m is mass of the particle, and so you can say that this acceleration a will be equal to F over m. So now we will make the use of this equation in above equation, and we will write instead of a f by m. So using this you can write the above equation easily. So our equation is now written as del f by del t plus v dot, I am not turning the page every time because now this equation will definitely be in your mind, so I am writing directly without showing you in another page. So v dot del f plus what? Instead of a, now we will write f over m, and dot, you know there is del v, which is gradient in velocity space f, and that is equal to what? That is equal to simply del f by del t collision, and for collision I am writing only C. And so what will be the equation number? C. This is equation number 3, you can say. Now this force may be actually any external force produced by the any external field, but here I am talking about a particular external field, and that external field is actually electromagnetic field. So if we consider that this F is solely due to the electromagnetic field, then you know in an electromagnetic field a charged particle experiences a electric and magnetic force, and the sum of the electric and magnetic force acting on the particle is known as Lorentz force. So if we recognize that this F is simply the Lorentz force, so if F is recognized, it is not necessary that we should recognize it as Lorentz force, but I have written if we recognize, if F is recognized as Lorentz force, then you know Lorentz force is what? This is actually the sum of electric and magnetic force, and you know this is, if Q is charge of the particle, E is electric field, then electric force will be QE, and magnetic force is Q times V cross B. You know this B is actually magnetic field and E is electric field. These are common symbols, so there is no need to write the meaning of it, but I am writing it here. This is in fact electric field, you know it, and B is what? This is actually magnetic field, and we have assumed that actually the external field is electromagnetic, and so in that condition the force acting on the particle will be the sum of electric force QE and magnetic force QV cross B, and this sum is actually known as Lorentz force, and you may write it as, taking the Q as a common factor, Q times E plus V cross B. This is actually the the Lorentz force F. So if we consider that our plasma is subjected to the Lorentz force, then what will be the equation 3? So you can see, instead of this F, now we will write this expression. So in this condition, you can say equation 3 will be now written as del F by del T plus V dot del F plus, instead of F you will write this much, so this will be what? This will be Q over M times E plus V cross B, E plus V cross B, and dot del Vf, so write here del Vf, and this is equal to what? This is equal to del, see here, this is equal to del F by del T at collision, and actually this very equation, when we have assumed that our plasma is subjected to electromagnetic field and the charged plasma particle experiences only the Lorentz force, then this equation has this form, and this particular equation is known as Boltzmann equation, not Boltzmann-Vlasov equation. It is only known as Boltzmann equation. It means when you will consider that electromagnetic force is acting on it, and you consider that collision is affecting the particles of plasma medium, then this equation is known as Boltzmann equation. So this is nothing, this is Boltzmann equation. Boltzmann equation. Now actually the Lasso equation is nothing, that is simply a special case of this Boltzmann equation. So Lasso equation is also known as Boltzmann-Vlasov equation, as I have written in the heading of this lecture. Boltzmann-Vlasov equation. So you may call it only Lasso equation or Boltzmann-Vlasov equation. Actually, what Lasso considered? Lasso considered a particular situation in which the effect of collision can be neglected. So when the effect of collision will be neglected, that is, you may say that collision is not changing the velocity of plasma particle randomly, in that condition we will say that our distribution function will remain unaffected of collision because we are neglecting the collision. In fact, when we will neglect the collision, then this Boltzmann equation will become Lasso equation. So since this Boltzmann equation is found from, this Lasso equation is found from Boltzmann equation, so it is also called Boltzmann-Vlasov equation. So, but when you can neglect actually the collision, you know, you have studied in the previous lectures that if we consider that our plasma is extremely hot or the plasma is at very high temperature and the particle density of plasma is very low, very small. Actually, in case of a hot and thin plasma, we can easily neglect the effect of collision. So let us consider now a plasma which is at very high temperature and its particle density is very low. So you can say in case of plasma at high temperature and low density, low particle density, you may say, low particle density. You know, you have already discussed such things in the previous lectures. In this, if these two conditions are satisfied, that temperature is very high and particle density is very low, then actually collision is negligible. So in this case, collision can be neglected, and if collision will be neglected, what does it mean? It means now you can't say that collision is affecting the velocity, and if velocity will be not affected by collision, then the distribution function is also not affected by the collision, neglected. So in this condition, this f of RVT will be not affected by collision, because now collision is not taking place, and therefore what will be this term? Del F by del T equal to del F by del T collision will be equal to 0. So if you assume that there is a plasma at very high temperature and in this plasma the particle density is very low, in that condition this term del F by del T collision becomes 0. So under this condition, what will be our Boltzmann equation? So Boltzmann equation in this condition, Boltzmann equation in this condition, is what will be this? You can see easily. Only the term in RHS will be now 0. We will make this term 0, and there will be nothing, no change in the LHS. So this will be simply equal to del F by del T plus V dot del F plus Q over M E plus V cross B dot del Vf is equal to 0. So this is the most important equation, or you call it a basic equation of kinetic theory of plasma, and you can see this is just a special case of Boltzmann equation. But this assumption was taken by the scientist Lasso. So this equation is also known as Boltzmann-Vlasov equation, or simply Lasso equation. So this is Boltzmann-Vlasov equation. Sorry, here should be not in fact A. V Lasso. Lasso equation. This is Lasso equation or Boltzmann-Vlasov equation. And as I have told you, this equation is actually known as kinetic equation of plasma. Actually, this Boltzmann-Vlasov equation finds a vivid applications, not only in plasma physics but also in condensed matter physics. And we also studied the application of this Lasso equation or Boltzmann-Vlasov equation in case of condensed matter physics. So what are the important uses? I am talking about actually the usage in plasma physics, usage of Lasso equation. Lasso equation. Actually, in this lecture, I am just going to mention its usage, but all usage we will discuss in the forthcoming lecture in detail separately. So, see, the first use of Lasso equation is to derive the dispersion relation for electron plasma wave. Deduction of dispersion relation. Dispersion relation of electron plasma wave. This is its first application, and we will see this application in detail in the next lecture. And another most important use of this Lasso equation is to discuss Landau damping. This is very important application of it. Landau damping. We will also discuss this Landau damping in very detail in the forthcoming lecture. The third one is actually the deduction of equation of motion of plasma fluid. This is also very important application of this Lasso equation. So the next one is deduction of equation of motion of plasma fluid. So these are basically the three most important applications of Lasso equations regarding this kinetic theory of plasma. And as I have told you, we will discuss all these three applications in very detail in the forthcoming lecture. But as I have told you, this Lasso equation or Boltzmann-Vlasov equation also finds its application in while dealing with the transport properties of transport properties in case of metals and or you can say semiconductors. And so we will also see the application of these equations in condensed matter physics. But in present context, our aim is to discuss its application only in context of kinetic theory of plasma. So we will discuss in the forthcoming lecture these three applications. So I hope you have understand each and every step of today's discussion regarding the Lasso equation. And if you feel any problem in understanding, you may write your problem, your doubt in comment box. Definitely I will rectify that.